Hello, in this video, we're going to be going through lesson 6.3 on conditions for parallelograms. The essential question that we'll answer is how do you prove that a quadrilateral is a parallelogram? There are 5 different conditions for parallelograms, and each of these conditions is a way to prove that a quadrilateral is a parallelogram. Let's start with the first condition. If one pair of opposite sides of a quadrilateral are both parallel and congruent, then the quadrilateral is a parallelogram. So in our picture here, notice that BC is parallel to AD as marked by the arrows, and we can also see that BC is congruent to AD because of those tick marks. So if that is what we're given, we would be able to conclude that ABCD is a parallelogram. The second condition for parallelograms is if both pairs of opposite sides of the quadrilateral are congruent, then the quadrilateral is a parallelogram. So this time it's important that we have both pairs. So you can see in this picture that side AB is congruent to CD. They're each marked with 1 tick mark, and the other pair of opposite sides, BC, is congruent to AD. And these theorems, by the way, don't have special names, so when we use them, we're just going to call them the theorem number. The third way that we can prove a quadrilateral is a parallelogram is if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. You'll notice in the picture here that angle A is congruent to angle C, and those are opposite angles. They are across from each other. And we also have angle B congruent to angle D. The fourth way that we can prove that a quadrilateral is a parallelogram is if an angle of a quadrilateral is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. So in our picture right here, we're going to focus in on angle A. Notice that angle A and angle B are supplementary because angle B is just 180 minus angle A, which is X. Right? Supplementary, as we know, just means they add to 180 degrees. Also notice that angle A and angle D are supplementary. So we need both of those cases to be met in order to use this theorem. So you have one angle, angle A, and it's supplementary to both of its consecutive angles. That then can be used to conclude that the quadrilateral is a parallelogram. The final condition that can be used to prove that a quadrilateral is a parallelogram is if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Bisect means they're divided into equal parts. So notice that my 2 diagonals intersect at point Z. What this is saying is that diagonal BD is bisected. Notice that BZ is congruent to DZ. And also notice that AZ is congruent to CZ. So because the diagonals are bisected, we get those matching parts, right? That makes the quadrilateral a parallelogram. So these 5 conditions are going to be really important. We're going to use these theorems throughout this entire lesson to justify if something is a parallelogram or not. Let's go ahead and try an example. Let's verify that the figure is a parallelogram, and we want to show that JKLM is a parallelogram when A is equal to 3 and B is equal to 9. Notice that the sides here don't have numbers on them, but we have values for A. So what we're going to do is we're going to start by calculating the measures of these. So for side, for example, JK, it's 15A, but I know that A is 3. So we just need to calculate 15 times 3 minus 11. And when you do that, 15 times 3, subtract 11 is 34. Then I'm going to do the side across from it, side LM. And side LM is 10 times 3, add 4. I'm just replacing the A with the number 3. So 30 plus 4 is 34. So there I have one pair of opposite sides that's congruent. Let's go ahead and check the remaining side. So let's go with KL. So this side up here, KL, is equal to 5B, and B is 9, so 5 times 9 plus 6. And when we do that, we can put it in our calculator or do it by hand here. We end up with 51. Similarly, I'm going to calculate JM, and JM is 8B, so that's 8 times 9 minus 21. You can put that in your calculator, and when you do that, you'll get 51. So now we have both pairs of opposite sides are congruent. These two are both 34. And the 51 and the 51 are another pair of opposite sides that are congruent. So using that information, JKLM is a parallelogram by, and then I'm going to look at my theorems list, and theorem 632 states that if both pairs of opposite sides of a quadrilateral are congruent, then it's a parallelogram. And we've shown right here that both pairs of opposite sides are congruent. Let's try another example. We'll show that PQRS is a parallelogram when x is equal to 10 and y is equal to 6.5. The first thing I'm going to have you do is calculate the angles. So let's go ahead and calculate the measure of angle Q, which is 6y plus 7. We're given y is 6.5. So I need 6 times 6.5 and then add 7. And that's going to be 39 plus 7. So we have 46. So the measure of angle Q is 46 degrees. Now go ahead and pause the video and then calculate the measures of angle R and angle S. Please pause your video now. So here I've calculated the measures of the angles. Angle Q was 46 degrees, angle R was 134, and angle S was 46 degrees. Notice that these two angles right here, if I add them up, 134 plus 46 is 180. So those are consecutive angles that are supplementary. Same thing right here, if I add them together, 46 plus 134 is also equal to 180. So if you go back to your theorem list, we have if an angle is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. Well, we've just shown right here that angle R, which is 134 degrees, is supplementary to angle Q and angle S. So since 134 plus 46 is equal to 180, we have angle R is supplementary to both angle Q and angle S. And if you look at your theorems list, this means that PQRS is a parallelogram by theorem, and it's 6-3-4 from your theorems. So pause the video and make sure that you finish filling that out, and then we'll move on to the next example. For this next example, we're going to apply the conditions that you filled out at the beginning of the lesson, that's the 5 theorems, to determine if each quadrilateral must be a parallelogram. The quadrilaterals all have markings on them. Congruent sides, congruent angles, parallel sides. We want to see, is this enough information for us to conclude that the quadrilateral has to be a parallelogram? We'll justify our answer, which means we'll explain our answer, and if it is a parallelogram, we'll justify it with the name of the theorem or using the definition of a parallelogram. We defined a parallelogram in lesson 6.2, and the definition of a parallelogram is just a quadrilateral where both pairs of opposite sides are parallel. So let's begin by looking at this first picture. What you should be noticing is that these two sides with the arrows on them are parallel, and then these two sides with the tick marks are congruent. If you look at your theorem list from this section, in order to prove that a quadrilateral is a parallelogram, you would need one pair of opposite sides to be both parallel and congruent. This is not that. We need one pair of opposite sides to be both parallel and congruent. Here I have one pair that's parallel, one pair that's congruent, but it's not the same pair. So therefore, it's not enough information to prove that it's a parallelogram. If you check out the picture in part B, that should look more familiar. Notice that the diagonals are bisecting each other. They intersect at this point right here, and that point divides the diagonals into equal parts. This one and this one each have one tick mark, so it's divided into equal parts. And the other diagonal, it's divided into sections with two tick marks. So that means the diagonals bisect each other. So it's a parallelogram by, and then if I look at my theorem list, it's theorem 6-3-5. If the diagonals of a quadrilateral bisect each other, then it is a parallelogram. Problem C is probably the trickiest here, and it's because we're going to need to go back to some of the things that we learned at the beginning of the geometry course. To make it easier to talk about this figure, I'm going to name it P, Q, R, and S. So notice that these two angles right here that are marked with two arcs, see how those are alternate interior angles? Well, we have alternate interior angles that are congruent, and since alternate interior angles are congruent, we know that these two sides, PQ and RS, must be parallel. And that's by the converse of the alternate interior angles theorem. Now this next one, I need to get angles congruent for the other parallel sides. So I would love it if I could do another pair of alternate interior angles. So if I look at the top and the bottom that I'm outlining in purple, I would love it if I could get angle 1 and angle 2 here to be congruent. Well, notice though that also there are two triangles in this picture. Each of the triangles, PQS and RQS, involve angle 1 and angle 2. So angle 1 has to be congruent to angle 2 by the third angles theorem. And now, since angle 1 is congruent to angle 2, and they are alternate interior angles, once again, we know that QR must be parallel to PS. Again, using the converse of alternate interior angles. So now what I have here is I have one quadrilateral and both pairs of opposite sides are parallel. So PQRS is a parallelogram, and this time it's by the definition of a parallelogram. The definition of a parallelogram is a quadrilateral with two pairs of parallel sides. The final example here, the try now, should be a little bit more obvious. As I look at this picture, I notice that there's two pairs of congruent sides, but also notice that these are not opposite sides. In order to prove it's a parallelogram, we would need both pairs of opposite sides congruent. And these two problems, or these two sides right here, are not opposites. They're consecutive sides. So this figure is not a parallelogram. This brings us to our last example, and we're going to get into some coordinate geometry here. So we're going to look at quadrilaterals still, but we're going to look at them in the coordinate plane. Remember from algebra that in a coordinate plane, two non-vertical lines are parallel if and only if they have the same slope. So as we move through these problems, if I can show that two lines have the same slope, we can conclude that those lines are parallel. So let's go ahead and start by plotting the points here. And you're going to need your graph to be just a little bit bigger to get up to 7. So on your y-axis, let's just extend this 2 more spots. It goes up to 5. I need to get up to 7. So just extend that a little bit higher. This is my y-axis and my x-axis. And remember that our ordered pairs always go x, y. So I need to go to -3 on the x and +2 on the y, and that's point A. And then point B is at -2, 7, right here. Point C is at 2, 4. And point D is at 1, -1. So there I've drawn my quadrilateral, and I want to prove that it's a parallelogram using the definition of a parallelogram. This is in your notes for lesson 6.2, and basically what I need to show here is you need to show that you have two pairs of parallel sides. And you're going to show that sides are parallel by comparing the slopes. So let's go ahead and start with the slope of AB. Slope of side AB, we can calculate it using our slope formula, which we learned last unit. It's y2 minus y1 over x2 minus x1. So that's going to be a very important formula for you to have whenever you're calculating slope. Change in y over the change in x. Now I also want you to remember that the first point is x1, y1, and the second point is x2, y2. So if I very carefully plug those numbers into my formula, we end up with 7 minus 2 divided by -2 minus -3. That double minus will switch to a plus, and we'll get 5 over 1, which is 5. So the slope of AB is 5. Let's check the slope of its opposite side, CD. Using the same formula for CD, again, I'll let my first point be x1, y1, and the second point x2, y2. We can go ahead and subtract our coordinates. So I have -1 minus 4 for y2 minus y1 all over 1 minus 2. And when we subtract those, we get -5 divided by -1. Remember that a negative divided by a negative makes a positive. So this is just going to reduce down to 5. Now we have parallel sides. Okay, because those are both 5, we have the same slope. So we can conclude that AB must be parallel to CD. They have the same slope, so let's mark that in our picture. AB parallel to CD. Now I just need to get the second pair of parallel sides. So I'm going to do the exact same thing. And I'm going to calculate the slope of BC and the slope of AD. Using our slope formula for BC, we have 4 minus 7 over 2 minus -2. And that reduces to -3 over 4. That minus makes a plus. Let's check out the slope of AD. So I'm looking at this point and this point. That's going to be -1 minus 2. That's the difference in the y's, divided by 1 minus -3. And when we simplify that up, we end up with -3, and then our denominator is 4. So just like we expected, we have two sides that are parallel again. So this is also the same slope. So we have the second pair of sides, BC, is parallel to AD. Let's mark that in our picture, BC and AD. And now I have both pairs of opposite sides that are parallel. So ABCD is a parallelogram by definition of a parallelogram. We have one last example to look at. Please plot those points. And there is what your parallelogram should look like. This time we want to use theorem 6-3-1, condition for parallelograms number 1. And this theorem states that you have one pair of opposite sides are both parallel and congruent. So I'm going to choose to focus in on FG and HJ. I just think that's easier because the points are right next to each other. So in our picture, we'll focus on FG right here and HJ right there. Go ahead and calculate the slope of FG and the slope of HJ. Please pause your video and do that calculation. When you do your slope calculations, you should have found that the slope of line FG, segment FG, is equal to 4/2, which reduces to 2, and the slope of HJ also reduces to 2. So we have the same slope, and that is enough information to conclude that FG is parallel to HJ. So now we've shown that we have one pair of parallel sides. I'm going to mark that in my diagram here. FG is parallel to HJ. Now I just need to show that they're congruent. And to show they're congruent, I need to show that they have the same length. So we need to calculate the length of FG. And to calculate the length of a segment, you can use the distance formula that we learned previously this unit. The distance formula tells us that the length of a line segment is equal to the square root of x2 minus x1, quantity squared, plus y2 minus y1, quantity squared. Now, the nice part about this is we kind of already did these calculations right here. So when I look at FG, x2 minus x1 is just -2 minus -4. We already did that again, but we just got to make sure we square it. Y2 minus y1, we also already did. 2 minus -2. Minus minus makes a plus. So here I have 2 squared and I have 4 squared. This whole thing is still under a root, so I'm going to just square those values. We have 4 plus 4 squared is 16. So the length of FG is the square root of 20. Let's check the length of the opposite side, HJ. Please pause your video now and do the same calculation for the length of segment HJ. When you do that calculation, you should have found that they both end up being the square root of 20. I don't need to get a decimal answer if I can just see that they're the same. So the lengths are equal. So we have FG is congruent to HJ. So now I have shown everything that I need to show. I've shown that we have one pair of opposite sides, and those opposite sides are both parallel and congruent. Let's actually mark the congruent sides in our picture. They're both square root 20, so they are congruent. And therefore, FGHJ is a parallelogram by, and then if you look at the theorems, it is theorem 6-3-1. That is, we have one pair of sides, opposite sides, that are both congruent and parallel. And this concludes lesson 6-3. Thanks for watching. Bye.